Welcome everyone to this Meet the Experts talk. The slide is now, the title is now slightly different to the original one, but just to make more clear what the content is of today's talk, and that is to give a practical guide for social scientists on how to tune large language models when you are dealing with limited resources. And I think this applies to most of us. And we're then especially looking at the so-called adapters approach. And after this talk, you should know what this approach is about. But let me first give you some information on myself. So I am working, as Danitza already said, as a postdoc in the Computational Social Science Department at GESIS. And more particular, I'm working in the data science methods team, where we develop methods to support social scientists. And my research interests are the development of inclusive AI systems. Especially, I'm interested in machine learning models that can represent the diversity of opinions in populations instead of only majority opinions. And I'm also interested in the development of efficient and accessible data science methods, especially for the social sciences. On a more substantive side, I am working on argumentation and deliberation, and especially I'm interested there in how to measure the quality of argumentation and deliberation, and then also whether we can improve the quality with computational methods. Okay, so our plan for today is to learn about adapters, but in order to do so, we first need to have a look into modern language models. We need to have a look into what fine-tuning is and why we need it, despite all these great LLMs that we can use out of the box. And then in third, we will finally look into adapters. You will learn what it is and why it's beneficial. And then we will also look into some example applications to make more clear how and for what scenarios we can apply adapters. But first, let me motivate why we should use LLMs for social science research. Text is one of the most widely used data resources in the social sciences. And if we want to conduct analysis on text data, especially at large scale, we need powerful computational methods because we cannot do this manually anymore. And this is where modern language models come into play, because they demonstrate a great potential for a variety of social science research tasks. And here are just some examples where LLMs have already been applied to successfully, and that is the coding of open-ended survey questions, the development and validation of self-report scales, or the annotation of textual data with social science concepts such as persuasiveness, political ideology. You can extend this to hate speech, etc. And in this context, I would like to point you at two resources at GESIS, where you can learn more about large language model use for social science research that goes beyond what we are covering in today's talk. So here, on the one hand side, you have the guides that are providing you with insights on certain topics. And then I also would like to point you at to the Methods Hub, which is a platform at GESIS where we collect ready-to-use methods. And then in tutorials, we provide you introduction into how to use these methods. So what are modern language models actually? Language models are not new. So here you see the full history from over 100 years ago until now. And the first language models already came into play in 1913. So what you see here is the Markov model. And more generally, a language model is a model that assigns probabilities to upcoming words or sequences of words. So it's a very, very general concept. Over the years, there have been quite some developments in the field, and the most important development of the last years was made in 2017, and that was the attention mechanism that was introduced. And this is also the basis for all the great modern language models that we have nowadays. So what is behind this attention mechanism? We will not go too much into detail, but just to help you grasp why this was such a milestone in the development of language models. So just imagine how you yourself process a paragraph if you read it. So what you do actually is, in order to understand its meaning, you focus on the most important words. This is what your brain does in the scanning of the text. And this is then exactly what these attention mechanisms also bring the model to do. So instead of treating every word equally, this was what the previous language models were doing. With the attention mechanisms, these models can now pay attention to those words that matter most in a certain context or for a certain task. And this mechanism has significantly improved the model's ability to represent and generate human language. And for example, think about ChatGPT. This is a model that relies on this mechanism. So the general model family that uses attention is called transformer models. And this is the transformer model architecture, and I know it looks probably super scary, and there's a lot behind it, but we do not need to understand all the details. What I will want you to understand within the next 2 slides is just the very basics of how such a model processes data, and then what the so-called model parameters or model weights are, because this is essential for adapters. So the very general data flow through this architecture is that we start from some textual input. So this could be a sentence from a news article, for example. This sentence is then cut into smaller pieces, which are called tokens and subtokens. And these little pieces of text are then represented numerically in the so-called input embedding. So you're having some numerical vector. And this numerical representation is then led through all the architecture from the input to the output. And what happens on this way is that this representation is being transformed and more transformed and more transformed until it yields what we want as an output. And so in the output, the model produces something that is specific to our task. So for example, if you're thinking about the survey, open-ended survey question coding, think about you're having a schema of, let's say, 10 categories that you would want to assign. What happens here is that then such an open-ended answer is sent through the model, and in the end you're having probabilities per category. So for each of the 10 categories, you get a probability whether the text belongs to that category or not. So this is a very basic processing of within transformer models. So the second thing is now about these parameters and weights. And this is important for the transformation of the numerical representations. So all these transformations are happening in the so-called layers. If you look at the orange, yellow, and the blue boxes here, you have a multi-head attention, an add-a norm and feed forward, So these are all a bit different ways of transforming the numerical representations. But the general idea is that in each of these blocks that we call the layers, you find so-called model parameters. And these model parameters, they determine how the input is transformed. And let me exemplify this a bit. So for example, if you are somewhere in the middle of this transformation process and your input at this point is a vector consisting of or having 1, 2, and you're in this layer you're having a parameter matrix as displayed here, then it's a simple matrix multiplication, for example, that transforms your input to an output, and so on and so on. So I put a specific calculation example here because it's essential for adapters that you understand that there are parameters in the model and that they are the essential part for capturing knowledge that is required to perform some task. And these weight matrices, they are not just randomly there, they are determined during the training process. And what we focus on in this talk is the fine-tuning process, but I will explain a bit more about this on the next slide. So for now, the takeaway should be that the parameter and weights in a model have to be set during training, and that they are responsible for how the model works for a certain task. Okay. So, as I already briefly mentioned, training means that we adjust the model parameters that you just saw, but there are hundreds, thousands, millions, billions of them in the models, that these model parameters are adjusted to improve the performance on a given task. And by the way, the task maybe most intuitive is the language generation that you see in a ChatGPT. So this is then also a task, and you want the best performance that you can get on that, for example. Therefore, you need a training. So most commonly, there is this so-called pre-training fine-tuning paradigm on how to train these LLMs. And the first step is a pre-training. So this means that the models are trained on large amounts of data, such as Wikipedia, news article, etc., almost everything that you can get. And the goal is here to build a generalist knowledge of language. And this step is also mostly done by certain stakeholders that have the computational power. This is nothing that we can do. And then in the fine-tuning process, we are normally taking these models that are already very good in general knowledge of language, for example, which words should follow each other, or which sentences are semantically related, and so on. So this is what the model has learned in the pre-training phase. And now in the fine-tuning, the models are trained once more. That means we adjust the model parameters and update them once more so that the model is even better working for our specific use cases. And this is one example for hate speech, how this would work. So on the left-hand side, you see an out-of-the-box model, some LLM that you can use through API, through a chat interface, whatever. So this is not fine-tuned. What you see here is that it may work for some instances. So the kill them is detected as a hate speech, but then the user is not detected as hate speech. So this shows already that there should be some, or is some improvement is needed. And what we can do is then this fine tuning, which means that we're taking a data set that has been annotated for hate speech, and we update the models to work well with this data set. And in the best case, in the end, we're having a model that can now better detect hateful instances. Okay, so I'm coming back again to ChatGPT. I mean, we probably all worked with it at some point, and it's pretty amazing, right? So why do we then need the fine tuning at all? Like, is this example that I showed with hate speech really a thing? Or can we just use LLMs out of the box? Unfortunately, we cannot, because there are still certain cases where these LLMs are not performing well. And this is for specialized tasks. I put here as an example the analysis of opinionated texts. For example, if I'm working on argumentation, I still see that there are some minor or major flaws with LLMs. But then it's also about, for example, specific domains. So if we're thinking about translation in general, these models are already quite good. But if we're then thinking about translation in a specific context, such as population surveys, where we may have a specific way of formulating things, or different requirements that the translation needs to fulfill, then these models can fail. And this also extends to other cases, such as languages or dialects that have not been in the pre-training data, or also sensitive data that has, of course, or let's hope, has not been in the pre-training because it should not be available. And in these cases, you still need to fine tune to get a good performance for your task. And this also brings me to one important remark at this point. Although there is a wide variety of LLMs on the market, we can only fine tune those where we have open parameters. That means that we can see the weights, and these, like the metrics that I showed you before, where we can really see what's in there, and then where we can also do changes to this. And the second challenge that is posed to us through fine-tuning is fine-tuning, especially of these modern language models, is their size. And if we're talking about size, it's always the parameter count. So the metrics, the weight metrics that I showed you in this little toy example, this was just a like very, very small one, but this is not realistic. Normally they are way bigger. And for example, here you see that the DeepSeek model can have 671 billion parameters. And also other models are still in the billions. Yeah, you have very few that are in the millions, most are in the billions. So this is, I think, very clear that this is a huge amount of parameters that need to be updated in the training. So here on the right-hand side, you see an overview of how the parameter numbers of these models have developed. And this only goes until 2024, but the trend remains the same. So just because these big companies like Apple, Meta, Microsoft, OpenAI, Google, and so on, they have the access to computing power, to more computing power, they go for the bigger is better. So they develop bigger models just because they can. And with bigger models, this poses the problem that we have more parameters that we need to update also in the fine-tuning. And in detail, this means for us, if we are doing fine-tuning, we will need some GPU for sure anyways, but this increases the GPU requirements and also the GPU memory requirements significantly. We have to handle longer training times. Then this also means that we are facing higher energy costs, which may also collide with our own demands on sustainability. And then we are having a greater storage need also for saving the final model. So once we're having the model fine-tuned, we also want to save it and maybe make it accessible to other researchers. And this is just one example for a llama with 7 billion parameters. So the GPU memory is in the gigabytes, 28 to 34 is here the estimation. You will also need several gigabytes here, 14 to store the model. I think it's very clear that this is a lot of memory space. And well, it should take several hours of training, but this is also, of course, very dependent on your training data set and the task, etc. So this is just a very rough estimate here. Okay, and this now leads us finally to adapters. So we have seen that the main issue is the number of parameters that need to be updated in the training. Therefore, the idea here is, or in general, of the so-called parameter efficient fine-tuning, which is the overarching idea that adapters also fall under, but there are also other methods. So the idea here is that if we reduce the number of parameters that we need to update during the fine-tuning, then we can make the computation more efficient and finally also feasible. Because many of the models we can simply not run. I mean, even a Llama 7B, which is not one of the biggest models, is mostly or almost not possible for like the standard user to fine tune. Yeah. So this is what ChatGPT outputs if you ask about a symbolic picture of parameter efficient fine tuning for a broken social scientist. So I found it quite funny. This is why I let it here. But yeah, let's have a look deeper into adapters. Okay. So the idea of this parameter efficient fine tuning is that we want to reduce the number of trainable parameters. And how do adapters do this? They add more parameters at selected parts of the model, which is at first quite counterintuitive, right? Because why should more parameters help you to reduce the number of trainable parameters? But what adapters do at the same time is that they freeze the remainder of the original model. That means that all the original model parameters remain fixed. They are not getting updates during the training. And you can see this in this draft picture. So the gray parts, this is the original model. This is just a screenshot of some layers within the model. And you see that the model parameters, the original ones, they are fixed, they are not updated. And then you insert some new parameters that are now here in blue, and only those are getting updated. And well, by the share of the gray and the blue, we already get quite like some feeling for that the new parameters should be less. But in the next slide, I will make clear why we have a really strong reduction of trainable parameters. But what I also want to add here is what is very cool about this adapters idea is that we have this cost reduction because we have less trainable parameters. But at the same time, we are not touching the general knowledge that is already encoded in the model, in this pre-trained language model. And this is really cool because otherwise something can happen that is called catastrophic forgetting. And that means that we're just overwriting the language, the knowledge that has already been encoded in the model. So we're losing information. But here, this information is kept, it's just fixed, and we're having new parameters. Okay, so the first trick that adapters do is the freezing and adding. But there's a further trick that ensures efficiency, and that is this specific architecture, which is called the bottleneck architecture. And I think it's pretty clear, right, from the picture why it's called a bottleneck architecture. And so on a high level, the idea is just that you create a bottleneck that reduces the number of trainable parameters through a down and up projection. Yeah, so I think easiest to understand this, because I know this, having this just in a 30-minute presentation is quite a challenge, but I think easiest is if we look at an example. So in this example, the original layers of the model had a dimensionality of 768, right? And we're now reducing it. In this example, it's a 24. And then what we do is that we're having two matrices, one or weight matrices. One is the down projection and one is the up projection. And both have these 768 times 24 parameters. And if we compare this to a matrix that, I hope you can see my mouse now, but that would be full here. That means that we would have 768 times 768 parameters, right? If we would not create a bottleneck here, then we would have almost 600 trainable parameters. Yeah. So this is the basic idea of an adapter. So this is the last slide about where I bother you with architectural images. But now that we have this bottleneck architecture, we can also think about where to add it into the general transformer architecture. And in this, you're quite free. You can add it almost wherever you want. You can add it sequentially, as you see with the A holds B architecture and the B5 architecture, but you can also add it in parallel. And this is not very theory driven, right? So how these different architectures evolved was that people were just trying and testing whether it's working better or not. So there's not too much theory behind. But these three architectures that I show here have been found to work quite well. So to sum up, the advantages of adapters and of the parameter efficient fine-tuning in general are that the trainable parameters, those that are costly, are reduced from billions of parameters to only a fractional amount. So, I mean, it depends on how you implement the adapters and how much reduction you want or also need. But I think a rule of thumb would be to reduce to 1 to 5% of the original parameters. And this then helps us to lower the GPU requirements, This shortens the training times. This then, of course, also lowers the energy cost, and it requires less storage needs for saving the models, because we only need to store those parameters that have been newly added and updated, because the original model parameters just stay the same. So we do not need to store them because they are anyway stored in the original model, and we can later just stack the architecture back again. And the best about this is that it's not only making fine-tuning feasible for us, but then it's also oftentimes comparable to full fine-tuning in terms of performance. Or we're only having slight deviations from the full fine-tuning performance. And coming back to the Llama 7B example, so we see that the GPU memory is lower and the model storage is obviously a lot lower. And this is, I think, also interesting, for example, if you in your institutions think about creating or fine-tuning models and then also releasing them, and you want to host them maybe yourself. So I think this is also an important consideration. Last thing about adapters, before we go to the practical examples or use cases, is the implementation of adapters. And unfortunately, while Python offers several libraries, there is, at least to my knowledge, in R no such an equivalent. So the recommendation is to work with Python. And if you're already working with the Hugging Face ecosystem, which I assume to be the most easiest for machine learning, then you can simply use adapters. This is an easy integration, and you just need to add a few lines of code. And this will be very intuitive for you if you have already worked with the transformers library with the Hugging Face ecosystem. And what is good about the adapters library is also that you do not only have these adapters that we learned about today, the bottleneck adapters, but they also offer a range of other methods for parameter efficient fine-tuning. For example, LoRa is a very famous one. And you can just plug and play. So that means you do not even have to or read all the papers about these methods, right? You can simply first just try and see how they work. So I think it's quite user friendly if you code in Python. And within the next month, there will also be a tutorial on how to implement adapters, especially for social scientists, that will be released on the GESIS Methods Hub. So if you're interested in implementing them, then please also have a look into that tutorial. Okay, so now let's look at 3 example applications to end the talk with. The first one is just very general text analysis. So what I just want to say here is that whenever you need customized text analysis, then with adapters, you can enable the fine-tuning of even bigger LLMs. And this is now just a placeholder example with hate speech, but you can think about all the examples from the first slide, from the coding of open-ended questions to the modeling of other constructs such as persuasiveness, ideology, and so on. So the second example that I would like to highlight here, the second example application is that you can also use adapters to enable longitudinal analysis with LLMs. And Important to know as a background is that LLMs have only a static knowledge. So in the pre-training of LLMs, they are fed with all this data, but there's little anchoring in according to time. So this is, you do not really have an anchoring in with respect to time. And also at some point, so once the model has been trained, everything that comes afterwards in terms of data has not been in the pre-training data, right? So is not included. And as we as social scientists know, is that society changes. For example, the public opinion with respect or is shaped by certain events and developments in society. And the nice idea of this work is that with adapters, you have a feasible way to temporarily align models with a number of time spans. So because we have learned today that already fine-tuning one model is a lot of effort. But if you want to fine-tune a model, fine-tune several models, so for several time spans, then this is even less feasible, right? So you also see this in the bird picture here, or the several birds. The idea is here that you take a model. In this case, it's a bird model, but could also be a llama or so, and you're having one adapter per time span. So this here, here's a medieval bird or an ancient bird, a medieval bird, and a modern bird, for example. And then as the last application example that I would highlight here is that you can also use adapters to debias LLMs, because all the LLMs that we are working with, they are biased. So they encode, for example, stereotypical bias per definition because the data sets have these biases in there. So the model will also learn these biases. And if we have a bias in the model, then this will also lead to biased text analysis and also to biased text analysis results, which we, especially in the social sciences, really do not want. And therefore, one nice application of adapters is also that you can train adapters so they can incorporate the biasing knowledge without changing the pre-trained knowledge, but you can just have it as a modular add-on. And these three examples were, of course, now a super quick wrap up, but if you're interested in these, we can either discuss about it now in the Q&A session, or you can have a look into the papers for more information. Okay, and as a last hint, you can also, if at some point you want to know more about adapters beyond our Q&A now, you can always also consult me, for example.